Alright, so the purpose of this lab is to locate suitable areas for building a new hospital in Cuyahoga County in Ohio. Let's say after brainstorming and consulting with experts, you have considered 5 factors for building a new hospital in this county. The first one is population density. Obviously, the hospital should serve a large population. You can download the population information at the block group level across the United States from this website, arcgis.com. Then you can select out your study area, for example, Cuyahoga County, using clip feature in ArcGIS. And block group is the smallest geographic unit that Bureau publishes sample data, and each block group has a population almost between 600 to 3,000 people. I already have downloaded the block group level data, and also I extracted that for the Cuyahoga County. So if you open up ArcMap and then add data and connect to folder, GIS, okay, and raster suitability, add, and here we can see the block group shapefile. So if you open up the attribute table of the block groups in this county, first of all, you notice that we have over 1,100 block groups in this county, and then for each block group, which is one row or records in this attribute table, each block group is associated with several characteristics. For example, we know the FIPS, which is the federal number, is a unique number for each block group. And also we have the population information, we have the population for different races, we have population for different gender, different age group, median age for that block group, for the male and female, household information, and so many other characteristics associated with each block group. We may need to compute population density, which is population divided by area. And also pay attention that this is a vector layer. And as you know, vector data are in the form of the point, line, or polygon. Here we have the polygon information. But we need to convert it to the raster grid for raster overlay analysis in this lab. The next factor is land cover type. And land cover can determine the cost of construction. For example, developed areas might be easy and suitable for building a new hospital, but wetlands or forests might be not suitable or expensive for building a new hospital. We have obtained land cover data from mrlc.gov, and in this website, if you go click on data and then downloads, and here, if you scroll down, we need to find the latest land cover data published, which is for the year 2019. And according to the description, NLCD, or National Land Cover Data, provides nationwide data on land cover and also change of the land cover at a 30-meter spatial resolution. Okay, so which means that each pixel shows 30 meter on the ground with 16 class legend. Okay, so if you look at this website, which is from MRLC, so it shows you the legend. For example, the pixel value of 11, it shows that it's open water. 12, it's ice or snow. 21 is developed areas, and so on. But I already downloaded the NLCD data, which was a very, very large data set, and then I selected out Cuyahoga County using clip function in ArcMap. But if you go to the ArcMap and then click on add data, and here you can see, you can find land cover raster grid. As you can see, it's a grid, so it's not a point, line, polygon, it's not a vector data. And if you select that and then click on add, so you'll notice that, so if you open up the attribute table, so the value 11, according to the legend here, it shows that it's open water. 12 shows ice or snow, and so on. Okay, and also it shows you how many pixels have the value of 11 counts. Okay, how many pixels have the value of 21, and so on. Okay, so if you let me show you the this land cover. So based on this one, we can decide is this appropriate land or no for building a new hospital. The next factor is proximity to major roads, and major roads are primary and secondary roads. And it is evident that accessibility to hospital is important, as people should have easy access to the healthcare. Where can I find road information? So if you go to the Tiger Line website, and then if you go to the web interface, and 2020 is okay. And then here, if you scroll down, you can find roads and then click submit. So here you can find the primary data for the entire United States, or you can select primary and secondary data, for example, for the state of Ohio. And then when you click download, it gives you the primary and secondary data for the state of Ohio, and then you can clip that for the Cuyahoga County in ArcMap. And again, if you go to the ArcMap, add data, you can find the roads information, roads SHP that you already clipped that with this Cuyahoga County. Click on add, you can see the primary and secondary road data. So the next factor is the slope, and the steeper the land, the higher construction cost. And we didn't have the sloped data, but we can download the elevation information from USGS. So if you go to the USGS website, if you scroll down and find elevation products, so here you can specify the resolution or pixel size. So 1 arcsecond equals to 30 meter spatial resolution. And you can also find the data as get the data at a finer resolution, for example, 1/3 arcsecond, which is 10 meters. But as you remember, the land cover data, the resolution was 30 meter. We're going to use a consistent pixel size for all factors. So I'm going to select this one, 1 arcsecond DEM. I'm not going to have this one. And then if you area of interest, if you select your area of interest, I'm going to use selectable polygon, and here I'm going to have the based on the county. Here, for example, for the Cuyahoga County is here. Okay, so it's for Cleveland, Cuyahoga County. And then if you click on search product, so it has the information for 1 arcsecond. If you go back here and then select 1/3 arcsecond, so when you do the selection, for example, for Cuyahoga County search product, it gives you for, so here is 1/3, which is 10 meter spatial resolution. So 1 arcsecond is appropriate and is sufficient. So I click on download link, but remember that we need to, here we need to remove this Lake Erie part of the Cuyahoga County. So again, I can use the clip feature for the raster data. So now if you click on download link, so it will download the USGS with 1 arcsecond spatial resolution for you. If you click on download link for this one, it's going to be 1/3, which is 10 meter spatial resolution. Sometimes you may need a higher resolution, but for this lab, 30 meter is sufficient. So if you go to the ArcMap and then click on add data, I already have removed the water section. And if you click DEM and then add, so here we have the digital elevation model, which is elevation. Remember that this is just elevation, it's not a slope. We need to perform some extra analysis to derive a slope from digital elevation model. And for digital elevation model, as you know, each pixel represents elevation. Okay, so each pixel, when you click on that, so this one has the value of the 207 meters above the mean sea level, and so on. So let me change the color ramp, so here we can better see the changes of the elevation. Let me use, for example, this one, and I'm gonna say that the green shows the lower land, and then red shows the higher elevation. So here we can see that as we are closer to the Lake Erie, we have a lower elevation, which makes sense. The final factor is the distribution of other hospitals, because we need to reduce the health disparity. And the new hospital should be somewhere not too far from the other hospital, but not too close from the other hospitals. So we need to consider that in our analysis. And for the hospital information, I obtained hospital shapefile from this website, which also they have obtained the information from the ODH, Ohio Department of Health OneSource. And we want to limit our analysis to only hospitals. So this shapefile has the hospital and also nursing homes, correctional facilities, but we're gonna just focus on the hospital. So we're gonna exclude this nursing home, correctional facilities from our analysis. Again, I have already done that using the select by attribute. I only have selected the hospitals, and then I export this one as a separate layer. And also it is for the entire Ohio. I already have clipped that based on the Cuyahoga County as the clip feature. Now, if you go to the ArcMap, add data, you can see the location of the hospitals, the distribution of the hospitals in this county. Okay, so after conceptualization and also formulation, which is brainstorming and also where you can locate the data, after you collect the data, we would like to overlay these layers based on these given weights. Okay, so let's say we obtain this weight based on consulting with experts, and these are based on the opinion of the experts. For example, population density has the highest weight, has the highest importance for building a new hospital, but land cover has the lowest importance in building a new hospital, but it still is very important factor. So, or you can obtain these weights based on the regression. So the coefficients estimation of the, for example, for the linear regression, so you can obtain these values as the weights in your analysis. Here is the flow chart that shows the steps that we would like to take. First of all, from block groups that we have downloaded, we need to have population density, right? Which is population divided by area, but it's in the vector format. It's in the polygon format. But we need to convert this to raster. As I mentioned, everything has to be in the raster format. The next one is land cover. Land cover is already in the raster format, so it's going to be easy. The next one is road data is in the vector format. It's a line data. So we need to first find the distance to road, which generates a raster grid. And after that, we have to rate it. That I'm going to talk about that in the next few minutes. And then we have digital elevation model, which shows the elevation, but it's not the slope. So the next step is that we need to convert or obtain the slope information from the digital elevation model. Then it's going to be in the raster format. Hospitals are in the vector format. We need to find the distance to hospital, which generates a raster grid. Okay, so after we converted everything to raster, you cannot easily combine these factors because first of all, there are in different units. Okay, for example, the population density unit is individual per square mile. This one is based on the mile. This one is based on, for example, degree. So you cannot combine or overlay the layers that are in different units. And also how we can say that higher population density is better. How we can say that closer distance to road is better. So we have to rate or score each factor, okay? So 0 shows it's not suitable, okay? 2 shows very low suitable, 4 shows low, 6 medium, 8 high, and 10 very high. We're going to use this common scale for each of these layers for scoring or rating, okay? And after we made all layer unitless, we can easily combine them based on this given weights that are based on the opinion of the experts. So let's begin our analysis. So first of all, we need to activate a spatial analysis. If you go to the customize and then extensions, here you need to check a spatial analysis. If it's not checked, you need to check a spatial analysis and then close. And the next thing is that we want to limit our calculation to the Cuyahoga County, okay? And also we want to set the pixel size consistent, which was 30 meter for all layers, okay? So how we can do that? So if you go to the Geoprocessing and then environments. So the first thing is that processing extent. I'm gonna have the extent as a block group. Okay, so the extent of our analysis is gonna be block group. And also for the raster analysis, so the cell size is gonna be 30 meters. So I click on as a specified below, and then I put the value of 30 meter, and the mask is gonna be your block group, which shows that we want to limit the calculation to the block group, not outside of it. And then click OK. Okay, so let's begin with the first factor, which was population density. So for the block group data, when you open the attribute table, we had the population information, right? What we need to have the population density. I think pop SQMI shows the population per square mile. Let me check that. So how can I do that? If you add the field, and I'm gonna create a new add a new field. I'm gonna add using the floats or decimal number, and here I can find the using calculate geometry. I can find the area for that. So if you click on a square mile, then OK, it shows you the square mile for each block group. And then if I add another field, and I'm going to call this pop dense, so the result of our analysis should be very close to the SQMI, okay? And if you click on float, it's not exactly the same because of the projection, different projection that is being used, but it has to be close to that one. So pop density is going to be, if I use field calculator, it's going to be the population divided by area that I just calculated. And if you click OK, so for example, this value is 3,315, and pop SQMI for this one is 300, so it's almost close to this value. Okay, so I'm gonna remove this one because it's not that accurate, because we have done some projections on the data. I'm gonna remove this field, and I'm gonna use the pop SQMI as the population density. So if you, for example, let me turn all layer off so we can better see the results. So we have the block group data. Let me show this map based on the population density, symbology, quantities, and then based on pop SQMI. Okay, apply OK. So here, so let me flip the color ramp, Philip ramp. So here we have higher population density. Here we have lower population density. And but this one is in the vector format. Okay, so how can I convert the vector data to the raster data? Again, everything should be in the raster format. So if you click on search, or if you can't find it here, you can click on this one, search. Here you can type feature to raster, and feature to raster, it converts the feature to a raster dataset, and your feature is going to be your block group. And then based on pop SQMI, and here I'm going to save it. Just remember that save everything in this folder. I'm going to save this as pop dense. It shows the population density, and you can see that the cell size is automatically 30. So because we already set this value in the environment. So now if you click on OK, so this one is still running. If you want to make sure that it's running, if you go to the Geoprocessing and then results, so here it shows that this one is still working. Okay. All right. So it converted the feature to raster. Now if I look at the pop dense, if I change the color ramp, for example this one, and then invert it, So again, it shows that the value that are in the red color, they show that they have a higher population density. So what's next? Population density has a unit which is individual per square mile. Okay, but for combining layer or for overlaying layers, we can't combine, for example, population density with land cover type. And how can I say that higher population density is better? Because hospitals should be built in a place that serves more people. And the answer is that using reclassify function. If you type reclassify here and reclassify spatial analyst, so what happens in reclassify? First of all, it makes the raster unitless, so which means that we are able to combine them. And also we can rate or score each factor. Okay, so if you click on reclassify, and your raster is going to be your population density, and we're gonna use the common scale for all factors. If you click on classify here, we're gonna have 6 classes here based on natural break classification. And then so it changes the break values, and also here we can show it can show you the distribution. So here between these values is going to be the first class, between these two is going to be the second, and so on. So here we can see for the last class between these two values we don't have many observations. So this one is a histogram. If you click OK, so the values between 0 and 1200 population density is very low population density. So we're gonna replace it with the value of 0, which shows that not suitable population density. So between these two values is gonna be 2, this value is gonna be 4, 6, 8, and 10. So the higher population density is better. That's how we can rate or score each factor. The next thing is that, so for the no data, it's going to be no data. And then we have to, here we have to do not use the default geodatabase. You need to save it in your own folder. So I'm going to call this reclass because it shows that we made this unitless. It's a reclassified raster, and then I use pop dense. So here we can see I've got an error because the number of characters is too much. So let me remove a few characters, pop D. So now we don't have a problem. And we're gonna change the missing values to no data, and it's okay, and then click OK. Okay, so as you can see here, we have lower population density. It gets the value of 0 in terms of population density. But here, for example, here 10, 10, 10, right? So we have higher population density. So we scored or rated, and now it's unitless. It's not based on the unit of the individual per square mile. So we made this unitless, and also we were able to rate this factor. So the next factor is land cover. Okay, so let me remove the pop dense because we have the reclassified value, and also for the block group I don't need this one. So the next one is land cover, and land cover is already in the raster grid format, and each pixel for the land cover, each pixel shows a specific type of land cover. But the only thing that we need to do is that we have to rate or score it. Okay, so we have to say that, for example, I don't know, ice area is not suitable. Okay, so how can I say that? We have to again use the reclassify. So since this is already in the raster format, we can directly convert this to, we can directly reclassify it. So if you click on reclassify spatial analyst, and this one is going to be for the land cover. The values for forests are not suitable. Okay, so 41, 42, if you look at the legend, okay, so 41, 42, 43, they're not suitable. So I'm gonna assign the value of the 0 for the forest, okay? So 41, 42, so if first click on unique if you already haven't done that. So 41 it's gonna be 0. 42, it's gonna be 0. 43 is gonna be 0. 81, 82, they're gonna have very low suitability, 2 and 2. And 20 and 52 and 31, 52, it's gonna be 4, and also 31, 4. And 23 and 24, it's gonna have the value of 6, medium, 6 and 6. And 71, which I think was grasslands, gets the value of 8. And 21 and 22 gets the value of 10. Okay, the highest priority, and the reason is that because they were developed area. But how about the value of the 11? So the value of 11 was open water. You can never have your hospital on open water, right? Or on also, for example, you cannot have your hospitals in the wetland areas. Okay, so I'm gonna set these values as no data. So 11, so the way that I will type no data is NO, but D has to be capital, okay, no data. And also the value for the 90 and 95 also has to be no data. So what does this mean? It means that when we have the value as a no data, so this is called exclusionary variable or exclusionary value, which means that it will remove the cells with the pixel value of the 90, 95 from all future calculations. Okay, so it's going to be no data, and it's going to be no data in your final result as well. So let's check the values: 10, 10, 6, 6, 4, 0, 0, 0, 4, 8, 2, 2. And then I'm going to save this as reclass underscore LC, which means Landcover, change missing value to no data, and then OK. The next thing is that I can easily remove the Landcover from the table of contents. Okay, so the next factor is a slope. And for a slope, we only have digital elevation model, okay? We don't have a slope. How we can get the slope or derive a slope from elevation? We know that a slope is derived from elevation. If you here type slope, and here slope spatial analyst, your raster is going to be your digital elevation model, and then your output is going to be a slope. And based on degree, everything looks good. Z factor, if it's 1, the default value is 1. It means that the x and y unit and z unit are in the same unit. And for us, all of them are in the meter. So 1 is okay. And the output is going to be 30 meter spatial resolution because we already said that. So click on OK. So very simple, it converts the digital elevation model to a slope. So we can easily get the slope information from digital elevation model. And the next thing is that how can I, because this one has a unit and also it's not unitless. And also how can I say that the flat areas are better? Again, we have to use the reclassify function. Again, here if I type reclassify, or if I go back, I already have reclassified spatial analyst, and here it's going to be a slope. So I'm going to say that the flat areas are the best for building a new hospital, while the areas with a slope, for example, above 6 is not recommended. So we have to remove the areas. So I'm going to treat slopes above 6 degrees as exclusionary values, which means that they're not going to be included in future analysis. There are going to be no data for the final result. So I'm going to click on classify. So I'm going to have 7 classes, and based on manual technique. So manual technique is that I define the break value. Okay, so if I click on manual technique, so I'm going to say that less than 1 degree is one class, between 1 and 2 degrees another, between 2 and 3, 3 and 4, 4 and 5, between 5 and 6, and don't change the last one. Anything after 6, I'm gonna set them as exclusionary values, and then click OK. And here, so here I have to replace the old values with the new values based on the scale that we had. So the values under 1 degree, which means the flat areas, they have the highest priority for building a hospital, so it gets the value of 10. So between 1 and 2, 8, 6, 4, 2, 0, and above 6 is going to be exclusionary value. Okay, so it's going to be no data, and here everything looks good. I can store it in the same folder, raster suitability, as reclass underscore slope, and then change missing data, missing value to no data, and then click OK. So now I can remove the slope, and also I can remove the digital elevation model. I don't need them anymore. So the next one is proximity to existing hospitals. So we have hospitals here, right? But the function that we're going to use for that shows the proximity to existing hospital is called Euclidean Distance. So if you type Euclidean and then Euclidean Distance Spatial Analyst, so what happens with Euclidean Distance? First of all, it generates a raster. So here we have a point, which is a vector data. First of all, it generates a raster data, and then each pixel in the raster grid, it shows the distance to the nearest hospital. So I'm going to have the hospitals our input, and then I'm going to say this, that the output is hospital underscore distance. So it shows the distance, each pixel is the distance to the nearest hospital, and everything else looks good to me. Click on OK. So what happens? So it generates a raster, and each pixel in the raster shows you the distance to the nearest hospital. So if you use, for example, measure tool based on miles or meter, doesn't matter. So it shows that how close they are to the hospitals. Okay, and also if you look at the identify value, so for example, this one, the value is based on the meter because the map unit is meter. So it's 2000 meter to the nearest hospital. So for example, this one is going to be more than that, 4000, okay, in this category, and so on. So again, this one is based on meter. The values are based on meter. How can I make this unitless? And the answer is reclassify. Again, I have to reclassify the hospital distance. And for the hospital distance, it's kind of tricky because it's not good to be very close to the other hospitals because we should reduce the health disparity and serve more people that are far from hospitals. However, being too far from other hospitals is also not good because hospitals normally share facilities, they normally share personnel, equipment. So the average distance between the hospitals, not very close, not too far, gets the highest score. Okay, so here, if I click on classify, I'm going to set the number of class to 7 and use the natural break classification, and OK. This value gets the value of 0, so it's very close. It's not good, distance to other hospitals, so 0 is not good. So I'm gonna set the value like 4810 and then 10840. Okay, so it's gonna be 0, 4, 8, 10. So this one is on almost average distance to other hospitals. And here again, it's going to be 8, 4, and 0. Okay, so it's too far. It's not good for building a hospital. It's too close. It's not good, but its average distance is the best. And I'm going to save this as reclass and underscore hospital, but I'd have limitation in number of characters, so I just call it hosp. And then change missing values to no data, and OK. So as you can see here, so for example, here is not too close to hospital and it's not too far from the other hospital, so it gets the value of 10. But when you are very close to the hospital, it gets the value of 0, for example, this area. And for example, if you're too far from the other hospitals, like here, again, gets the value 0. And the last one is proximity to major roads, which is similar to proximity to hospitals. And we will use Euclidean distance. So let me remove the hospitals and proximity to major roads. So this is our roads. So I'm going to use the Euclidean distance. Euclidean distance. So your input feature is going to be your roads, and your output is going to be roads underscore dist. So each pixel shows the nearest distance to the roads, and the output cell size is 30, and then click OK. So the closer to roads, so first of all, it generates a raster grid, so which is good for overlay analysis, and each pixel shows the distance to nearest road. Okay, so for example, this value based on the meter is 1200 meters to the closest road, and so on. Okay, so for example, this pixels are too far from the nearest road, so the value is going to be like 4,600, 4,400, and so on. So again, how can I say that if you are closer to roads, it's better for building a new hospital? You have to reclassify it to make it unitless. Again, if you go back to reclassify spatial analyst for the road distance, and it's gonna be, if you click on classify, I'm gonna have 6 classes here, and based on the natural break, and then click OK. So when you are very close to the road, it's better. So it's gonna be 10, 8, 6, 4, 2. If it's too far from the roads, it's not good because of the accessibility problem. So I'm gonna save this as reclass underscore roads, and then OK. Let me remove roads and then full extent. So now all the factors have been rated and all of them are unitless, right? So let me remove roads distance. So everything is reclassified. So we have all 5 factors reclassified. All of them are in the same scale. All of them are unitless. And you are able to combine them. You are able to overlay them based on the weight table. And just to clarify, when we say weight is between factor. Okay, so here, based on the weight that we had, is between the factor, and rate or score is for each factor. Okay, so to overlay the rasters, to overlay these reclassified layers, the function that we will use is called raster calculator. Okay, so raster calculator spatial analyst. So I'm gonna multiply each rated or reclassified factor by its associated weight. Okay, and then I'm gonna add them up, divided by the total weight, which is 1. Okay, so I just want to multiply each factor by its weight, and I'm not gonna use the keyboard, just use the panel. Okay, so the first one was reclassified pop density, and this one has the highest weight, was 0.27, right? Plus the second one was reclassified land cover and multiplied by 15%. If you remember, this one has the lowest importance. Plus the next one was reclassify of roads times 19% plus, and reclassify of a slope times 17% plus, reclassify of hospitals times 22%. Okay, so this is gonna be your final suitability map. Okay, so I'm gonna call this suitability index or suitability map, and everything looks good. Click OK. So you will get a map like this, and the values are between 0 and 10. The values that are closer to 10, it shows that the higher suitability for building a new hospital. So let me change the color ramp. I'm gonna use this, invert this so the red shows the higher suitability. I'm gonna turn all layer off, just the suitability index. So it seems like, so for example, in these areas we have the highest suitability for building a new hospital. So one thing that you can do is that you can again reclassify this map on the scale of into 5 categories: very low, low, medium, high, very high, or just use this map. So I think this map is much better than the reclassified again. So we want to verify that is the result are consistent with our criteria or no. So first of all, it has to be very close to the major roads. Okay, so if I add, for example, our major roads, so you can see that it's very close to the major roads. Okay, these areas. That's good. It shouldn't be too close to the hospital, and it shouldn't be too far from the other hospitals. Okay, so if I add the hospitals, so these areas not too close to the hospitals, not too far from the other hospitals. Okay, the slope has to be flat. Okay, so if I add this slope from this area, yes. So, and then let me change it, for example, to, so the yellow means flat. Okay, so it's almost a flat slope. So if I change the color ramp, for example, to this one, again, it shows a flat slope, so which is good. So the land cover type should be, I think 21, 22 was for the developed areas, was the best. So let me remove this one. And for the land cover type, if I add the land cover and check this with land cover, 21 and 22 are this color. So as you can see, the land cover type for these areas are 21, 22, and also 23. So it's not, it can't be exactly the best, but 21 and also 22, very good land cover type for building a new hospital. And in terms of population density, if I look at the block group, and if I use the population, look at the population density, which was pop SQMI, so it has to serve the higher population, right? So let me change the, flip the symbol. So it has to be, as you can see, has the higher population density compared to the other areas. So it seems like for this area, the criteria have been met. So this was just an example for verifying the results are consistent with our criteria. But similar to the suitability analysis with vector data, so the next step is that you should have a field trip to the suitable areas. Probably there is a protected area here. Okay, so you can't have your hospital in these areas. Okay, so there are some other factors that you didn't consider in your analysis. And once you're happy with your map, once you're happy with your suitability index map, so you have to go to the layout view and then add the title, suitability map for building a new hospital, add the legend, north arrow, scale bar, your name and date, and export it as a JPEG file.